Okay, let's start our lecture with apparent depth. So what is apparent depth? When you look at an object that is inside water, the rays that um, go from water to your eyes um, are bent when they go from water to air. And you see here these rays going from water to air are bent away from the normal, and in order to see the image of the object in your eyes, these rays need to meet somewhere. Since they do not meet on this side above the water, that means we need to produce the rays backward, and when we produce the rays backward, so the rays meet at some point that is above the actual depth of that object. So it's formed here. That's the image. So we see here that this is the actual depth from the surface, but when we look at the object appears to be above the actual location. It's now here. So that means this distance from the surface of the water to that image is the apparent depth. Okay, so how do we find the apparent depth? Apparent depth could be found by using this formula. In this formula, d prime is the apparent depth, and this d is the actual depth, n2 is the refractive index in the second medium, and n1 is in the first medium. So the light originated from the object in water. That means n1 would be that of water. So this is the first medium, and the light went out in air, so n2 would be the second medium. So in this case, n2 is air, the refractive index of air, and n1 is the refractive index of water. Okay, so using this formula we can get the apparent depth of an object in water. Okay, so here is another example. So when the light rays originating from the object go out of the water in air, they are bent away from the normal. So you would have a normal here, and it's bent away from the normal. So you can have a normal here. It's bent away from the normal. Now on this side, the rays won't meet. That means we need to produce the rays backward to form the virtual image. So the image formed by producing the rays backward is what we call virtual image. So this is the virtual image of this object. Okay, and this depth is the apparent depth, d prime. So let's see an example. So you dropped your keys into a 2-meter deep swimming pool. How far down do they appear to be? So basically we want to find the apparent depth of the keys in the water. So that's the water. Okay, and so let's say you have keys somewhere down here. Now the rays originate from the keys. When they go out, they are bent. So the rays going out, bent, and when you produce these rays backward, so they will meet above the actual location of the object. So it will form here. So that's the image of the keys that you will see from above. Okay, so that's the apparent depth, d prime, and that's what we want to find. So d prime is the actual depth times refractive index in the second medium and refractive index in the first medium. Again, first medium is the medium in which the rays are originated. So this is the first medium, and second medium is the medium where the rays are refracted. So that's n2. So d is 2 meter actual depth, and N1 is the refractive index of air, which is 1, and the refractive index of water, it is not given here, but you can look the value of refractive index from your book. Okay, so that's 1.33. So if you do that calculation, you would get 2 divided by 1.33 gives me 1.50. So that's 1.50 meters. So that's the depth from the surface. Okay, 1.5 meter. Now let's talk about this thin lens equation. We started this last week, so last time. Let's now talk in a little bit more detail about thin lens equation. This equation is applicable to both lenses, concave and convex lenses, as well as to concave and convex mirrors. So this is applicable to both lenses as well as mirrors. Okay. However, we need to be a little bit more careful when we use this for all these different mirrors, and when we see different kinds of images. Okay, so there is sign convention that we need to take care of when we use this formula. Now, in this formula, F is the focal length, S is the object distance, and S prime is the image distance. Sometimes in some textbooks you may also see this formula as 1 over dO. dO is same as S. Okay, so that's the object distance, plus 1 over di, which is the image distance, which is same as S prime. Okay, so I will be using this formula because that's what we have in our textbook. Okay, we want to just follow our textbook, so we'll be using that. But if you see this formula in other textbooks, that would be same as the formula that we would be using. So now, what are the sign conventions that we need to consider when we use this formula? So let's look at that. So in this formula, so we have this formula 1 over F is equal to 1 over S plus 1 over S prime. So this F would be positive if the lens is converging, and it is negative if it is diverging. Okay, so that's the sign for F. So converging lens is it's the convex lens. So this convex lens converges the light rays, and diverging is this kind of concave lens. So this is the concave lens, which is the diverging lens, concave. Okay, in case of mirror, this kind of mirror is converging mirror. So for mirror, it's concave mirror, that's the converging. And this kind of mirror with this reflecting surface is the diverging mirror. So in case of mirror, it's convex mirror. Okay, so for convex mirror and concave lens, F is negative. For convex lens and concave mirror, F is positive. For the object distance, so again we are using S for that. So object distance would be positive if the object is placed to the left side of the lens. If we place the object here on the left side, then it is positive. Okay, if we have the object on the right side, then it is negative. Okay, in case of mirror, it's always on the left side. Okay, so if this is the reflecting surface, then that's where we will have the object. Okay, And if we have this convex mirror, this is the convex mirror, then this would be the object. So we usually place the object in front of the mirror. So usually for mirrors, object distance is always positive. Now how about the image distance? So here we'll be using S prime for object image distance. If the image is formed, if the image formed is real, then it is positive, and if the image form is virtual, then it is negative. Di is negative. Okay, for virtual, we consider the image distance to be negative, and for real image, it's positive. Again, real image is formed by real intersection of the refracted rays or reflected rays. In case of mirror, it's reflected rays, and in case of lenses, it's refracted rays. Okay, so actual intersection of those rays are those rays form real image. And if there is no actual intersection, and if we need to produce the rays backwards, then the image formed is called virtual image. Now there's another very important term that we often use in lenses and mirrors, which is called magnification. Okay, so let's define magnification. Magnification is basically how big or how small the image is with respect to the object. Okay, whether the image is magnified or diminished. That's what this magnification is. It is the ratio of image height which is denoted by HI, image height, over object height, which is denoted by HO. Okay. There is another way to find magnification. By the way, magnification is denoted by letter M. It is the ratio of height over height, so it's unitless quantity. It doesn't have any unit. And we can also find magnification by taking the ratio of a negative ratio of image distance over object distance. Okay, this is the object distance. So that also gives us the magnification, or in terms of di and do, we can also write this as minus di, image distance, which is distance between the image and the lens or the mirror, over yeah, that's right, and distance do, distance, this is the distance between the mirror or the lens and the object. Okay, so image distance over object distance gives us the magnification. If the magnification is positive, that means the image is upright, and if the magnification is negative, it is inverted. Okay, so let's look at number 6 from our worksheet. Let me copy the question here. So here is our question, and this question is basically asking to find the image distance for a combined lens. Okay, so we have a system of 2 lenses. So we have this convex lens, and we also have a concave lens or a diverging lens. Okay, so the focal length of this concave lens is minus 31.5 centimeters, and the focal length of this convex lens is 20 centimeters, and this concave lens is 14 centimeters behind the convex lens. So this distance is 14 centimeters. And we have an object at an infinity far away somewhere here, okay, an object somewhere here. So our object distance is infinity. Now when we deal with this kind of combined lenses, we can deal with the lenses individually, okay. So in this case, let's deal with the convex lens first. So for convex lens, our thin lens equation is 1 over f is equal to 1 over s plus 1 over s prime. And let's find out where the image is formed. So 1 over f, or I can modify this formula or rearrange this formula as 1 over s prime is 1 over f. I take this to the other side, it becomes minus 1 over s. Okay, just rearranging this formula. And I have 1 over f is 1 over 20 centimeters minus 1 over s. Now s is s is at infinity. That's infinity. And 1 over infinity is, infinity means it's a very, very large number, okay, big number. So 1 over a big number, let's say 1000 or something like that, that would be a 0. So whenever you divide 1 by a large number, that turns out to be 0, or a very small number. So we can consider this to be 0. So that means we have 1 over s prime is equal to 1 over 20 centimeters. So if I want to get s prime, then I need to flip both sides. When I flip both sides, I get on the right side s prime is equal to 20 centimeters. So that means this lens forms the image at 20 centimeters, somewhere here. Okay, and s prime is positive. Okay, if we see our sign convention, if s prime is positive, so let me go to the sign convention here. If d is positive, it's a real image. Okay, that means it would be inverted. Okay, so we know that usually real image is inverted. So it's formed here, but it's inverted. Now let's deal with this concave lens. So for concave lens, so the image of this convex lens, now this would be the object for this convex lens. Okay, so this is the image formed by convex lens, but now it's the object for this concave lens. That means the object distance for this would be distance between the object and the lens, which is this one, which is, so from here to here is, we just found that that's 20 centimeters. Okay, that's the image distance of the convex lens. And we also know that the distance between the two lenses is 14 centimeters. So this whole thing is 20 centimeters. That part is 14 centimeters. Then that means this part must be 20 minus 14, which is 6 centimeters. Okay, that's the object distance for concave lens. Now if we look at the sign convention, so let's go back to the sign convention. So d would be, or the object distance would be negative if the lens is, or if the object is on the right side of the lens. Okay, so in our case, the object is on the right side of the lens, so we need to put a minus sign for this object distance. Okay, and we know the focal length of this lens is minus 31.5 centimeters. Okay, And now we want to find the image distance, and we already know that image distance could be written as that. So 1 over f minus 1 over s. So this is again the meter or the lens equation. So 1 over f is minus 1 over minus 31.5 centimeters minus 1 over s is the object distance, which is 20 centimeters. Sorry, not 20 centimeters, my mistake. Let me correct that. So that would be minus 1 over, that's the object distance, minus 6 centimeters. So we have minus, and we have minus here, so I can multiply minus and minus, that becomes plus 6 centimeters. Okay, now let's do the math. So let's see what we get. So 1 over 31.5 gives me negative 0.03174 plus 1 over 6 gives me 0.167. Now do the math. .174, so that gives me 0.13492. Now I have 1 over s prime on this side, so in order to get s prime, I need to flip on both sides. Oh, okay, so when I flip on both sides, this would become 1 over 0.13492. Okay, and when I do the math, what I get 7.41 centimeters. So that's 7.41 centimeters. Okay. And so that would be the image distance for the concave lens. So if I go up here, so this concave lens forms, it's a diverging lens, so it forms virtual image. So usually the virtual image is on the same side, so it would be somewhere here. Okay, let's look at another problem. So this is number 3 from worksheet 4. So in this problem, we are given a concave meter with focal length of 20 centimeters. So let me draw a concave meter. So the concave meter has the reflecting surface on the inner part. So that's the reflecting surface, and that's concave meter. And its focal length is 20 centimeters. That means the distance between the optical center and the focal point is 20 centimeters. And an object is placed at 60 centimeters from the optical center. So our S, which is object distance, is 60 centimeters. And also given the height of the object, which is 3 centimeters. So we want to find where the image is formed. Okay, so we want to find S prime. We can use the meter equation. So meter equation is 1 over F is equal to 1 over S plus 1 over S prime. And we can rearrange this to write in terms of 1 over S prime. So that would be 1 over F. So taking this to the left side, it becomes minus 1 over S. And 1 over S prime is equal to 1 over F f is 20 centimeters minus object distance is 60 centimeters. Okay, so at this point you can use your calculator. You can just divide 1 by 20 and then divide 1 by 60 and subtract 1 from the other, and then you can take the reciprocal of your answer. But I'm going to do a little bit of math here. So the least common denominator here is 60 centimeters, and to get 60 centimeters I need to multiply this by 3, so I need to put 3 here, and to get 60 centimeters I need to multiply this by 1, so that's 1, and 3 minus 1 is 2, and that's 60 centimeters. So I can cancel that and that with 30 on the bottom. So I need to get s prime here, but I have 1 over s prime, so I need to flip on both sides to get s prime. So flipping on right side gives me 30 centimeters. Okay, so that's the image distance. And this is positive, so it would be inverted, it's real, and the concave mirror forms the real image on the same side. Okay, so it would be 30 centimeters from the optical center. That means it would be somewhere here, and it's inverted. Okay, so s prime is 30 centimeters, and we still don't know whether it's magnified or diminished. Okay, so now we will find the size of the image and the magnification. We already answered that it's inverted because it's positive, and also it's real. Okay, so let's look at magnification. Magnification is given by the negative of image distance, which is s prime over object distance. So negative of s prime is, we just found it, 30 centimeters, and object distance is 60 centimeters. So that means that's minus 1 over 2. Okay, so this indicates that the magnification is half. Okay, which means the image is half the size of the object, and this negative sign implies that it's inverted. So if we want to find the actual height of the image, we can do that. So magnification is height of the image over height of the object, and we have this magnification of 0.5. Height of the image over height of the object is 3 centimeters. So that means hi is minus 0.5 times 3 centimeters. So we do the math, we get minus 1.5 centimeters. That's the height of the image. And again, this minus sign means it's inverted. Okay? So this image would be diminished. It's smaller than the object.